Right now, without feeling a thing, you are moving, not around the sun, not around the center of the galaxy. You are being carried outward at hundreds of kilometers every second, away from a region of space that is emptier than it has any right to be. Here is the promise. By the end of this, you will understand why two of the most careful measurements ever made of our universe give two different answers, and why that disagreement may come down to a single uncomfortable fact about where we live. Here is the tension. Both measurements are precise. Both should agree. They do not. And here is the question that a small number of astronomers now take seriously, and that most people have never heard. What if we are sitting near the center of an enormous hole in the cosmos, and that hole has been quietly distorting our view of everything? For most of the last century, cosmology rested on one calming assumption. Zoom out far enough, and the universe should look the same everywhere. The same density of galaxies in every direction. No special places. No privileged address. Physicists call this the cosmological principle, and it is not a small idea. It is the foundation that lets us write simple equations for the whole universe and trust that they hold from here to the edge of what we can see. The principle earned that trust. It correctly predicted the faint afterglow of the early universe. It explained how galaxies gathered into clusters. It matched observation after observation with a precision that is genuinely rare in science. Then a measurement started to break. There are two clean ways to measure how fast the universe is expanding. The first reads the ancient light left over from the young universe and calculates what the expansion rate should be today. That method returns a number close to 67. The second method looks at nearby exploding stars and pulsing stars, whose true brightness we understand, measures their distances directly, and reads the expansion rate off the sky. That method returns a number close to 73. Those two numbers should be identical. They are not. They differ by about 9%. 9% sounds small. It is not. Both measurements have been refined for years. Their uncertainty shrunk to almost nothing, and the gap has not closed. It has hardened. The disagreement has now reached a level of statistical confidence where the odds of it being a fluke are less than 1 in a million. Cosmologists stopped calling it a discrepancy. They started calling it a crisis, and they gave it a name. The Hubble tension. Something in our picture of the universe is wrong. Either one of these measurements hides an error nobody has found, or our understanding of cosmic history is incomplete, or we are missing a piece of physics entirely. For years, the field has been split between those uncomfortable options. But there is a fourth possibility. It is stranger than the others, and for a long time, it was easy to dismiss, because it requires giving up something we told ourselves for 100 years. It requires accepting that our location is not ordinary, that we do not live in an average patch of space, that the very place we measure from is not typical. To see why anyone would take that seriously, you have to go back to 3 astronomers who were simply counting galaxies and found far too few. The work began with a quiet, almost old-fashioned task. Count the galaxies, measure how much light they give off across a huge volume of space, and compare the nearby volume to the distant one. If the universe is uniform, the density of that light should stay roughly flat as you move outward. That was the expectation. Ryan Keenan was a young astronomer working with Amy Barger and Lennox Cowie, studying the sky in near-infrared light. Near-infrared matters here because it cuts through dust and traces the mass of galaxies faithfully. It is one of the most honest ways to weigh how much matter actually sits in a region of space. They pulled together several of the largest galaxy surveys available and measured the density of galaxies as a function of distance from us. The numbers did not stay flat. Close to home, out to a distance of hundreds of millions of light years, there were fewer galaxies than there should be. Not a small shortfall. The local region held only about half the matter density of the distant universe. As they looked farther out, the density climbed back toward normal. The pattern was unmistakable. Our galaxy and everything near it sits inside an enormous, underdense region that stretches outward for something like 1 billion light years in every direction. The structure took the initials of the three who characterized it, the KBC Void. Across, it spans close to 2 billion light years, which makes it one of the largest underdense regions ever proposed, wide enough to cover most of the sky around us. Now, a void is not truly empty. This one still contains our galaxy, our neighbors, and vast collections of other galaxies. What defines it is not emptiness, but deficit. There is simply less here than the cosmic average demands. And that deficit is the problem, because in the standard story of how the universe grew, an underdensity this large and this deep should be extraordinarily rare. When researchers took the leading model of cosmic structure and ran enormous computer simulations of universe after universe, voids on this scale barely appeared. When they did appear, they demanded very unusual starting conditions. By one careful analysis, a void as large and as empty as the one we seem to inhabit sits so far outside expectations that ordinary gravity, working on the standard blueprint of matter, struggles to produce it at all. The mismatch was severe enough that some researchers argued it strains the standard model well past its breaking point. That is where the discovery stopped being a curiosity and became a confrontation. Because if the void is real, one of two things must be true. Either we happen to live inside one of the rarest structures in existence by pure chance, or the rules we use to grow the universe are missing something important. Both answers cost us something, and before you decide which one is easier to believe, you need to understand exactly what living inside a void does to the light and the motion we measure. Start with gravity, and one fact that sounds backwards until you sit with it. Inside a void, gravity effectively pushes outward. Gravity does not reverse. It always pulls matter toward matter. But direction is everything. Picture a wide, shallow valley ringed by higher ground. Stand in the middle, and the ground pulls you down toward the center. Now, change the setting. In a cosmic void, almost all the matter lies outside the empty region, in the denser walls of galaxies that surround it. That external matter pulls on everything inside. So, galaxies within the void are drawn outward, away from the center, toward the denser regions beyond the edge. The result is a slow, steady outflow. Everything inside the underdense region drifts toward the rim, and our galaxy is part of that motion. The Milky Way is moving away from the nearest empty stretch of space at hundreds of kilometers every second, pushed by the imbalance between the sparse interior and the crowded exterior. This is not the expansion of space. It is real motion through space, driven by where the matter is and where it is not. Now, connect that to the measurement that started all of this. When we gauge the local expansion rate, we watch nearby galaxies recede and read off how fast space is stretching. But if we sit inside a void, those nearby galaxies are not only riding the expansion of the universe, they are also being pulled outward by the void's own gravity. That extra outward motion adds to the signal. Galaxies appear to be fleeing faster than the true cosmic average. And so, the local expansion rate comes out too high. That is the idea that closes the gap. We are not measuring the universe wrong. We are measuring it correctly, from a place that is not typical. The nearby number is inflated by our own outflow. The distant number read from the ancient light that crosses the entire universe reflects the real rate. Two honest measurements, two different answers, because one of them is taken from inside the whole. This explanation makes a sharp, testable prediction. If a local void is inflating the nearby expansion rate, then the measured rate should depend on how far out you look. Sample only nearby objects, deep inside the void, and you should get the high number. Push your measurements outward, past the void's edge, and the rate should fall back toward the cosmic average. And when researchers sort their measurements by distance, that downward trend is what begins to appear. The apparent expansion rate is highest close to home and eases as we look deeper. It is exactly the pattern a void should produce. For a while, this looked like a clean solution. It fixes the tension without inventing new particles or rewriting gravity. It simply says our address is unusual. But that comes at a heavy price, and this is where the story turns. The whole foundation of modern cosmology was that we occupy no special place. Copernicus moved us off the center of the solar system. Later work moved the sun out to an unremarkable corner of the galaxy and moved the galaxy itself into an ordinary crowd. Every step of that history pushed humanity further from any privileged position. The void hypothesis pushes back. It says we live near the center of one of the largest, rarest underdense regions in the observable universe. After centuries of insisting we are nowhere special, we would have to admit that our location, at least, is genuinely strange. That discomfort has split the field into competing explanations, and each one asks us to give up something different. The first explanation is the void itself. Except that we live in a rare place and much of the tension dissolves. The cost is the assumption of an unremarkable location. The second explanation is bolder. Perhaps gravity does not behave exactly as we think on the largest scales. Some time ago, the physicist Mordechai Milgram proposed that at extremely low accelerations, the kind that dominate the outskirts of galaxies and the vast spaces between them, gravity grows stronger than our standard equations predict. Under that modified gravity, structure forms more aggressively, denser walls, deeper voids. In that picture, a void as large as ours is no longer a freak accident. It becomes something the universe should produce naturally. The tension eases, but the cost is enormous. It means revising a theory of gravity that has passed every other test thrown at it for over a century. The third explanation reaches for new physics in the early universe, or in the nature of the force accelerating cosmic expansion. Maybe that dark energy is not constant. Maybe it changed over time, adjusted in the right way, and the two expansion rates can be reconciled. The cost here is a new ingredient we do not understand and cannot yet detect directly. And the fourth explanation is the most deflating of all. Perhaps there is no deep mystery, only a subtle error, dust that dims distant explosions more than we account for. Stars that behave differently than we assume. Every time someone proposes this, the measurements are re-examined and refined, and so far the tension has survived. But it has not been completely ruled out. To feel the strangeness of living inside such a region, it helps to know how much of the universe is like this. When you imagine the cosmos, you probably picture a sky crowded with stars and galaxies. The reality is closer to the opposite. Galaxies gather along thin walls and dense knots, and those structures wrap around enormous empty regions. Taken together, the voids fill something like 90% of the total volume of space. Most of the universe, by far, is emptiness. The bright, crowded places where galaxies live are the exception, not the rule. Inside those empty regions, the balance of forces shifts. Where matter is abundant, gravity is strong enough to resist the expansion and slow it locally. Where matter is scarce, gravity is too weak to resist, and the force driving cosmic acceleration, the dark energy pushing space apart, takes over almost completely. So voids do not simply sit there. They expand faster than the rest of the universe, and as they grow emptier, they expand faster still. The underdense regions are becoming emptier with time. Follow that forward, and the far future looks lonely. As cosmic expansion accelerates, the walls around each void thin and stretch, and distant galaxies slip permanently out of view. A civilization born inside a deep void, billions of years from now, might look up and see almost nothing beyond its own galaxy. No distant structure, no evidence of a wider cosmos. They would measure their universe and get the wrong answer, with no way to know it. Which raises an uncomfortable question about ourselves. How confident can we be that we are not already living in a milder version of exactly that situation? Here is what makes the void so compelling and so frustrating. It leaves traces beyond the expansion rate. The same outflow that would inflate the nearby rate should also carry whole regions of galaxies along with it, creating large-scale streaming motions across the local universe. Those motions are observed, and they run faster and reach farther than the standard model comfortably predicts in roughly the direction and strength a void would demand. Several independent clues seem to point the same way, and yet the case is not closed. Recent work that traces the actual motions of nearby galaxies, using direct distance measurements rather than galaxy counts, suggests the underdense region needed to fully explain the tension may be far smaller than the original claim, perhaps too small to do the whole job on its own. The void may be real and still not be the entire answer. That is where the frontier sits right now. Not resolved, contested. Now follow the consequence that unsettles cosmologists the most, because it reaches all the way to the age of everything. The expansion rate is not just a number. It sets the timescale of cosmic history. A faster expansion means the universe reached its current size in less time, which makes it younger. Take the high local rate at face value, apply it to the whole universe, and the cosmos comes out roughly 1 billion years younger than the standard estimate. That creates an impossible situation. We can measure the ages of the oldest stars in ancient clusters by watching how far they have burned through their fuel. The oldest of them come out to around 13 billion years. You cannot have stars that are older than the universe that contains them. If the high expansion rate were the true global rate, the math would demand stars older than time itself. The void offers a way out of that trap. If the high rate is only a local illusion, inflated by our outflow, then the true cosmic rate is the lower one. The universe keeps its full age, and the ancient stars fit comfortably inside it. The paradox dissolves, but only if we accept that we have been reading the universe from a distorted vantage point all along. And that is the confrontation at the center of this. Every headline number you have ever heard about how fast the universe expands, how old it is, how much of it is empty, rests on a hidden assumption that where we stand is ordinary, that our measurements sample a fair piece of the cosmos. If we truly sit near the center of a vast underdensity, then some of those numbers are not universal truths. They are local readings, taken from an unusual room and mistaken for the whole house. We may be doing careful science with flawless instruments and still misreading the universe, not because we made a mistake, but because of where we happen to be standing. So here is where it leaves us. We have spent centuries removing ourselves from the center of things, learning again and again that we are not special, that our vantage point is ordinary. And now the sky may be telling us the opposite, that we happen to live inside one of the emptiest regions the universe has ever made, and that this accident of address has been bending our measurements the whole time. Maybe the void is the answer. And the crisis is really a lesson in humility about where we stand. Maybe it is only part of the answer, and something deeper in physics is still hiding. Maybe, when we finally see far enough past the edge of our own hollow, the universe out there will look nothing like the one we thought we knew. What we cannot do anymore is assume we are standing on neutral ground. Every number we trust about the cosmos was measured from one specific place. And that place, it turns out, may be one of the strangest in all of it. If we really are cosmic outsiders measuring a universe from inside a hole nobody told us about, what else have we gotten wrong simply because of where we happen to be looking from?